Hello class. Today we want to look at an application of the trigonometric functions, in particular the wave functions, sinusoidal, cosine, and sine will make a wave like this. And one application in nature that we find is the way sound works, and this tuning fork is an example. So when the tuning fork is vibrated, this metal prong is moving back and forth, and as it moves in this direction it pushes air together, creates density, and then it pulls back this way and leaves more space in the air. So we've got this alternation between higher density, lower density, higher density creates the sound wave, and that's the way we interpret the sound. So if we put the air pressure on the y-axis and the time, the air density changes along the way, and it wiggles your eardrum, and you interpret that. And so there's components of that that are built into what a function looks like. So let's look at those. Okay, so let's look at the important components of what creates this cyclical behavior. Here we're going to look at a spring that has a mass attached to the end of it, and if we pull it down, stretch it down here, and let go of it, if we don't have any friction to slow it down, it will continue this up-down behavior. And so it'll create this up-down behavior, and we'll have this cyclical result. It looks like a sine or a cosine. So the displacement, the distance it's displaced would be the difference between the rest and the highest point, called that amplitude. So this distance here and this distance here both represent amplitude. So on our graph, this is the rest position and this is an amplitude, and that represents an amplitude there, the distance here, same distance there. Okay, if we reference back to our circle approach for trigonometry functions, and we think of the angle theta, and the angle theta is going to basically sweep through this circle, and if we say that omega is the angular speed at which the angle sweeps through this circle, then that angular speed times time is going to give us the angle theta, and we'll work in radians here. And so if theta is equal to the speed times the time, of course at time 0 it's going to start right here at 0, but then as time goes by it's going to sweep the angle out all the way around this circle. And so we can interpret the cosine of theta to be the x-coordinate over a, because a is the amplitude, which coincides with what we thought of as the radius, and the sine of theta is y over radius, which is the amplitude. So if we calculate and solve this for x, we're just going to multiply the cosine of theta by the amplitude, a, out here. And then since we called theta omega times t, we can substitute omega times t here. So we've got our amplitude here, and then the angle that's swept out by angular speed of omega times the time. So this calculates our x coordinate at any given time, and this calculates our y coordinate with the given amplitude at any given time. Okay, so all we need to know is what's our angular speed. And so what's going to create, in this case, how speed is like, think of how fast it's going through its cycles. It's fast spring, or it goes down low, and it's a slow spring. Okay, so this is the graph, and this is our amplitude. So we have the amplitude, and this is the time at which it's reached that amplitude, and then it drops down. That's also an amplitude below. So this is the time when it reaches that. So as we're graphing this, we've created this notion of simple harmonic motion. And if we want to use cosine, then it's going to be the distance or the displacement from the rest position. So that's our y coordinate, right? So where we are on the y-axis, the distance, and then we'll come swing back up and just keep going through these cycles by the amplitude. And the amplitude is just going to be the absolute value of A, and the period, or the time it takes to complete one cycle, is, if we know omega, we just take 2 pi, divide it by omega, because 2 pi is the natural cycle of either the cosine or the sine. But if we're moving at a speed omega, angular speed of omega, then we're going to either speed it up or slow it down, and we'll call that period a capital T. Okay, one other thing that's useful in this scenario is the frequency, and that's easy to find if we know the period, because the frequency is just 1 over t, and since t is 2 pi over omega, the frequency is going to be the reciprocal of the period. Okay, so these are the parts that we're interested in: the amplitude, the period, and the frequency. All right, so let's look at a situation where we build a model that matches this scenario. So if we look at the way this starts, at the rest position, before anything kicks off, the spring is pulled down to -5. So we would think of that as A equals -5. Now remember, A is different from the amplitude. The amplitude is the absolute value of A. So the absolute value of A is 5. So that's our amplitude. But A that we use in the function is going to be -5. The other thing to consider is that it's at a full amplitude at the rest position times 0. So if we look at our two functions that are our options, the cosine is in red here and the sine is in blue. Notice that of the two, the only one that's at a full amplitude in its natural state is the cosine. So since we're going to take it times -5, that's going to drag it down here and flip that, but it will be at its negative amplitude down here, and then its positive amplitude through its cycle. So it makes more sense to use the cosine. So the model that we've decided on is the displacement with respect to time is equal to A times the cosine of omega times t, which is our angle. And in this case, we know that A is -5. They tell us here that a full oscillation is 3 seconds. So remember that a period is equal to 2 pi over omega, the angular speed. And so since 2 pi over omega, the period is 3 seconds, we can find omega now. So omega, if I solve for omega, I get 2 pi over 3. All right, so we can fill in our model now because we've got A, we've got omega, and then t is the variable on the horizontal axis. So we end up with displacement over the course of time is equal to -5 times the cosine of 2 pi over 3 times t.